Hi, everyone. Thank you for having me here. So, Applied Materials, Israel, I'm not sure everybody are familiar, so in one word, we are developing and producing tools for process diagnostics and controls and for the semiconductors industry. And I will try to shrink you into our tiny 3D world, and believe me, it's a jungle in there. So, Moore's law, Gordon Moore was already mentioned here today, and this is what drives our industry forward, trying to increase the performance in every couple of years or so. The law have changed with time to adapt to what the industry can do. Actually, this is what caused the trend of shrinking the transistor, and this is what allows you to use better algorithms, and us to use better algorithms, which allows the industry to shrink the transistors even more. So it's a cycle that as long as it keeps going, we have work. And this year, actually, Gordon Moore died, passed away, and also Intel, a couple of months later, announced that it's not keeping the pace with Gordon Moore's law anymore. But the industry is still investing a lot in order to try and shrink the device further. So what's being done in order to keep up? Traditionally, the industry moved to smaller and smaller devices using shorter wavelengths, argon fluid lasers, immersion techniques, sinking the wafer underwater in order to increase the numerical apertures of the microscope. Today they are talking about extreme UV, 13 nanometers wavelengths of the laser. Just creating lens is impossible in these wavelengths. They have to use mirrors, and also creating mirrors for these wavelengths is kind of crazy. Another trend is to increase the wafer size, because always real estate is expensive, and the bigger the wafer is, the more transistor you can put in one device. There was a trend to go to 450 millimeter wafers, quite huge. Currently it didn't stick, but it may come back. And the new trend is kind of like in real estate, to move from a flat building to building to the skies and utilize the height. And this is why we are in the 3D world. So up until 2011, everything was flat. So a transistor looked like this. We have a source in one side, a drain in the other side, a gate in between, and you apply voltage to the gate. You create a small tunnel where the electron pass from source to drain. In 2011, Intel came up with a transistor called the FinFET. So the structure here is the fin, and one side of it is the source, the other side is the drain, and the shape surrounding it is the gate. So what you are doing actually create a tunnel for the electron, which is much bigger, allowing better mobility of the electrons, reducing the resistivity, and allow you to shrink the device even further without suffering from heat and no mobility of the electrons. In 2013, the memory foundries, flash memory, DRAM, also starts moving to three-dimensional, and actually what they are doing today is stacking the bits one on top of the other and not one side to the other as they used to, in 40 layers, 60 layers, and they are talking now about 128 layers, and so on and so forth. And in the future, already in some labs, they started developing the nanowires solution, where the transistor is the tiny nanowire and the gate is the orange thing that surrounds it. So the world the semiconductor world is moving towards three-dimensional structures. And this is creating new requirements for the metrology business. And in order to really utilize the three-dimensional structures, the foundries or the equipment which is producing the FinFETs need good control, and they need to fully characterize the structures. What's their angle of the slope of the sidewalls? What's the height of the device? How rounded it is? Every little characteristics or such characteristics, at the end of the day, manifests in the electrical behavior of the transistor and the final performance of the device. Also in the VNAND area, the depths, the CD, or the critical dimension in the bottom, the critical dimension in the top, the slopes, also the roundness of the corners are very important in order to reach good performance of the device. So how do you retrieve 3D information from a semiconductor device? So you can fly a drone over it and use a LiDAR or a small camera below it. Actually, our 3D information looks a bit different than trees, and no, you cannot fly something above it. Just to get the scales right, so if this, for example, is a camera you use to create a 3D reconstruction image, we are looking on the chip here and the inner side of it. And if the scale we are talking about, bacteria is an elephant, okay? It's 1 micron. A virus is still very big. It's like a city for us, okay? It contains many structures or houses that we want to measure. DNA is getting there, okay? It's 10 nanometers, so this is more or less the current design rule, and it keeps shrinking. And why is the size so important? So obviously light is not an option. Photons are not producing the desired resolution. Even if we're taking relatively short wavelengths, which is already very difficult to manipulate with optics, you can get to 100 nanometer resolution, not much below that. So what's the alternative? How can we create 3D information from a semiconductor device in these tiny sizes? So electrons are our friends here. And there are several ways of using electrons, scanning electron microscope and tunneling electron microscope. I will describe the technology briefly in the next slide. And another technology is an atomic force microscope, which is kind of amazing. It can actually work in a very high resolution. Here you can see a molecule mapped with atomic force microscope. So how does those technology works? Atomic force microscope uses a very small needle. It's like a patifon, very tiny nanometer needle. And this needle is actually touching the device. It's following the device. It's moving and touching the device. The only thing that separates it from within the device is the atomic force. And using interferometry, you can look on the needle and see how it moves. And this is very precise. Scanning electron microscope, you have a microscope that makes the electron beam, controls the electron beam as you wish to make it very small in order to have resolution. This electron beam is fired on your sample, and the electrons that are extracted from the sample are collected to a detector, and this is what creates the images. And the transmission electron microscope, it's kind of similar, but the sample is placed in between. So you are going through the sample and can get kind of a CT image. The only problem here is that the electrons penetration is not very deep, so you need to cut the wafer and have a very thin piece and put it here. And our customers usually don't like that we cut their wafers. Okay? We are trying to improve their yield, not reduce it. The comparison between those systems, AFM is very, very accurate, and it's non-destructive, but it's very, very slow. Okay? TEM, tunneling electron microscope, is very accurate, but it's destructive. Okay? And slow, of course. And the scanning electron microscope is not very accurate, but it's very fast comparing to the other alternative, and it's non-destructive. So now I'll tell you in few words how we use scanning electron microscope to create 3D information from the device, to extract 3D information. So since we are building our own microscope, we have designed a microscope that has a detector that can collect the electrons according to the angle they come out of the wafer. So if we have a gun here that shoots electron down on the wafer, the electron that comes out of the wafer are coming out in Labertian with relation to the angle of the wafer. And if we looking on a flat surface, then we expect the electrons to be fully balanced between those detectors. And if we are looking on the slant area, then there will be some bias of the electrons. So we have created the proper mathematical framework for this, so we can reconstruct the surface from the amount of electrons that get to each of the detectors. And this is more or less how it works. So if you go and pixel by pixel and calculate the gradient from the amount of electrons that are distributed between the detectors, and then sum the gradients, so it's a height from gradient method, and you get your three-dimensional shape. So this is how our 4 quadrants images look like, and this is the 3D model reconstructed from them. So first of all, you can look at the images. You can see the light and shadow, and each of those detectors are this is the real direction of it, like 45 degrees from the sample. What's interesting to note is that it's different from usual the usual physical world where we are lighting, where the light source is what casts the shadow. Here, the light always comes from above, and the collection detector is what's being shadowed. So if we have a shadow on the edge of the left, it's because electrons that comes out of the sample do not reach the relevant detector. So a few examples of several devices, and also a few of the issues that we are suffering. So you can see, for example, some tilted or low frequency noise that we are not reproducing well. But generally speaking, we are getting very good 3D shape in relative short time. Another example, these are actually nanometer scratches, very, very small scratches, which are very difficult to observe without the three-dimensional reconstruction. How do we use this three-dimensional data? So segmentation, for example, if you look on the normal SEM image, it's very difficult to understand what's the upper side of the line and what's the lower one, but if you look on the 3D reconstruction, it's straightforward. And the classification is another example. Defects that look very similar in terms of shape, but if you want to understand if it's a crater or a bump, the 3D data is crucial. Challenges, so if the aspect ratio, if the width is very small compared to the height, not many electrons come out to the directions of our detectors, and then we cannot reconstruct there. Very steep edges, since we are doing height from gradients. If we do not have enough samples along the edge, then we are not reproducing the edge very accurately. And also calibration issues. Since we are reconstructing the 3D according to the distribution of the electrons, if we have a difference in gain or offset which are not coming from the actual electrons coming from the yield, from the sample, then it causes bias to the sample. And to conclude, 3D semiconductor metrology is an underserved market, so it requires a lot of innovation in order to keep the industry going. And if you have ideas, come to me. We are able to combine our scanning electron microscope technology with our physical understanding in order to produce 3D maps quite fast online. The 3D data is used in many applications: registration, segmentation, measurement, classification, and detection. And we still have many challenges ahead. Questions?